Okay, welcome to the section of graphing combinations of functions. After in the first few sections, which actually took quite a while, we encountered how to graph functions, and I kept my promise of that. Most time we'll be looking at cosine and sine, and rarely ever did we do the others. Here's going to be similar. We're going to look at sine and cosine again, but this time around we're going to combine them with each other and with something else. It's taking it a step further, so we're not just graphing one particular sign, but we put it into combination with something else. You will see at the end of this lecture that there are actually certain applications for doing that. So let's start first here with one. We're supposed to graph y equals 1/3 x minus sine x. And here's a description I wrote down. The upside down sine graph, that is negative sine x, lies along or hugs the straight line 1/3 x. I'm going to show you that in Paint. Oops, we actually have to first open something. There we go. There we go. All right. So here I'm first going to graphing 1/3 x, which is going to look like this: 1 up, 3 over. Okay, there we go. And the same in the other direction. And that's pretty good. Okay, so that's 1/3 x. Now what happens with the sine? Well, what we're going to have is, I think it was a simple sine, yep. So we're going to have a 0 point right here. Then the next x-intercept would appear at pi, so here, but now it's going to be on that line. And the next one would appear at 2 pi. So it would be here, but then it's going to be on that line. And it's going to be upside down, so I'm going to go like this here. So let me try if I succeed or how good it's going to look like. Do I choose yet another color? Oh well, here's purple. So I believe it's going to look something like this. And then it continues on. And that should be, actually maybe I'm going to do this large. There we go. So the resulting one will be actually this one here, and that continues on, and it's going to cross it again, and so on. Okay. Let's go over to the graphing calculator and see if that is indeed correct. All right. So it's at 1/3 times x minus sine x. Okay. And the window setting, I'm going to go to 2 pi. That's fine. Pi over 6 is the scale. My y minimum doesn't even have to be that small. Could be actually -1. I'll do -1. And then I'm going up over x equals 6.28, or I'm actually going up quite high to y equals 2. So I'm going to make this 3 here. And then we'll see what we get. Okay. All right. How does it continue there? You saw in Paint the way it looked like. So here's the 1/3 x. In fact, I might as well put the 1/3 x in there. There it is. There it is. And now you can actually see that sine x hugs the 1/3 x. Let me go to, perhaps 6 pi or so. I just went to 2 pi. So I'm going to go to, actually I will make this one here thick, the one that we really need to graph. And then in the window here I'm going to go to 6 pi which is 18. 18 times 1/3 is about 6, so I should put my y maximum to about 7 or so. And let's see what we get. So that's actually the sign on top of the 1/3 x, and as you can see, it hugs the 1/3 x. Okay. Let's see what we have in store next. We're supposed to graph x cosine x. We could almost think, gosh, isn't that kind of similar to what we just had? But a moment ago, it said in between a plus or a minus. This time it says a times, so x times cosine x. So let's see what happens in pane. Okay, I'm going to use this one here. And I'm going to have my cosine normally may look like this here. So I have here, there's the cosine, and then at 1.5 it reaches 0, and then at 3.1 is -1, and 4.7, and at 6.2 or so it's back. But instead it actually increases. At this value here, it's actually down to 0 simply because it's being multiplied by 0. So let me show that. I'm going to use a different one here, I guess. There we go. Here it's actually 0 again. Okay, but here's something different. Here we have the cosine is -1, but in the meantime, the x that's in front of it is 3. So 3 or 3.14 times -1, we're going to end up over here. Here again, we're going to have 0. Here we have 1, but in the meantime, the x is going to be 6. So 6 times 1 comes out to 6. All right, how does this one look like? Well, going backwards here, we probably come up with something like this. And then we probably have something like this here. So it kind of increases here, and probably its shape is going to go further down and larger and larger. So let's look at the graphing calculator. Let's see where we are. Okay, clear this one, clear this one. Okay, x times cosine x. And right now it's going up to 6 pi. I'm just going to make it 2 pi for now. That will still give me a relatively large range here, so I may want to go down to -7 to 7. All right, that might work. So there we go. And that's kind of what we saw a moment ago. And then, of course, we can go on with that and say, all right, what about if we go to 6 pi? So there we go. This one here, it's going to be really small. Make it pi. The scale. And then the y minimum, well, we have to look what the x maximum is here. So it's going to be roughly, I want to say -20 maybe to 20. And then there. That's what we saw so far. And as you can see, it gets larger and larger. And then, interestingly enough, what you can do now is you can go to y equals, and I'm going to make this a thick line. And down here, we're going to do a thin line for simply x. And, oh, I just leave it. It's okay. I want to make a dashed line, but I just leave it. And -x, and watch what happens. Okay, so there's the one that we really need to graph. And there's the x, and there's the -x. So the cosine is kind of going in between these graphs of x and -x, and -x should actually have an angle of 45 degrees, so maybe I'm going to do this z squared and see how that looks like. Oh, gee, maybe I didn't want that. Nah, I don't think I wanted that. That looks not too strange. Whoa. I'll go back to what I had here. 6 pi, I think that was. There we go. That looks better. Even though it's not a 45-degree angle as it should be. Okay. Let's see, the next problem. Next example of combining functions. We have graph e to the negative x sine x. How does that look like? Well, again, we're multiplying these two here just like we multiplied here. What we found out here is that the x here, the function in the front here of the cosine x kind of shows the cosine its limits. So it's very likely that the same thing is going to happen here, that the e to the negative x kind of shows the limit for the sine. Let's look at it in Paint. Okay, how does e to the negative x look like? Well, let's see what color I use. I guess I use blue. Well, it would start at negative at 1 here and then go down to 0, respectively, come out of the positive infinity and for negative x. I'm going to extend the scale here so it looks a little bit nicer. So let's assume that we have 1 here, and it goes through here, and it goes down here. And then what does the sine do? Well, the sine does the following. As the sine usually would be right here. And let's see, here, no, that's not true. Here and here, what it does is it goes like this. There we go. And then it's kind of hard to draw here. There we go, and goes on like this here, and goes on like that, and hugs the line here. And then we would have, again, another line that looks like this, roughly. So again, the e to the negative x is the limit for the sine. This doesn't look very good at all. Let's see on the graphing calculator. So we had e to the negative x times sine x. And the graph for that, actually, let's do this 2 pi to begin with. Okay, well, that really doesn't matter here. The y minimum in this case is actually really just going to be negative 1 and 1. And it approaches actually 0 really fast. When I actually have to graph, I'm going to do it a little bit different. I'm going to amend my problem here. Instead of doing it this fast here, I'm going to make a really small x in here, so 0.1 perhaps, and then I try that again over a period of maybe 8 pi. And let's see what we get this time. Okay, that looks a little bit better. There we go. Oh yeah, that looks way better if I want it. Okay, and again, we can make this a thick line, and then here we can plug in e to the negative 0.1 x and negative e to the negative 0.1 x. There we go. Okay, so there it is. What that actually is imagine a pendulum or a spring going up and down and getting slower and slower until it stops. And that's pretty much what this kind of equation describes. All right. Let's see, got a couple more in this lecture. So let's see, I did this one here, but I did amend it, so it was negative 0.1x in the argument for the exponential. Okay, this one here says y equals cosine x plus cosine 2x. How is that going to look like? Notice that I left out my paint, so I'm not even going to try it. In fact, what I'm going to do at this point here, because I'm already 20 minutes in, I will have a second part of this lecture, and this will be the first problem that we're going to look at. So I'll see you in a moment. Okay, let's go ahead with our lecture on combinations of functions and graphing them. So here we have cosine x plus cosine 2x. I'm just going to go to the graphing calculator and see what's happening with that one. Okay. So cosine x, as I had already mentioned, it would be really tough for me at this point to actually try this in Paint and figure out how it looks like. So we'll just look at it here. Let's look at the window. Let's start with 2 pi at first. Scale isn't really that important. We're adding the 2 cosines, so each of which has an amplitude at 1, so possibly they could go all the way up to 2 or negative 2. So let's see what we get. Okay, it actually kind of looks like a polynomial of 4th degree, where we have a relative maximum and 2 relative minima. Let's actually see how it looks when we extend the window. So let's do this here, 8 pi again, I guess. And it keeps doing this. So it changes kind of between small amplitude and large amplitude. Okay, let's go back to the lecture. So the function value changes between small and large amplitudes. Let's see what happens when the periods of the 2 individual trig functions are relatively close to each other. So this one here looks almost the same as the one above, except that as we have here 2x just as well, we have 1.9x instead of 1x as above. And that says here I should change the window from negative 100 to 100 for x, so I guess we'll see what happens then. So same kind of, virtually the same kind of function. So I'm just going to get in here and insert a 1.9 as a coefficient. Of course, we're looking at coefficients of 1.9 and 2, which means we're looking at periods of pi and tiny bit larger than pi. Okay, let's see when we graph. Okay, we can see a little bit over the span of 8 pi. Something is happening, it's decreasing. And then I made myself a note there where it said graph it from negative 100 to positive 100. And I don't know really if the scale matters. And let's see what we get. So this is pretty much what it's doing here. It goes from very large amplitudes to tiny amplitudes. If this was played as a musical note, let me copy this one here. If this was played as a musical note, then what we would hear is a large amplitude, so it would be loud, and then a small amplitude, so it would be quiet, and then loud, and then quiet, and so on. And pretty much what we have there is what is called a beat, that we're trying to match up a frequency, for example, of a tuning fork with the frequency or pitch of a tone of an instrument, and that's how an instrument is tuned. What the musician doesn't want is that particular beat. The amplitude shouldn't go up and down, listen to that beat. So what the musician is actually looking for is, when does that beat disappear? When will that 1.9 here match to 2? So what the musician would be doing is he would be trying, or she would be trying to change that coefficient B, or the period of the frequency that is being played, and therefore match the tuning fork, and therefore have the instrument tuned. And that's pretty much what I say here. Okay, let's look at one more thing. Whoops. Accidentally push myself completely somewhere else. Another application of combining trigonometric functions is by Fourier series, and they represent certain waveforms, and they can be used in physics and engineering and electronics to look at wave functions of electronics, for example. So here's one, and notice it looks really complicated. Pi over 2, that's just a vertical shift, right? Minus 4 over pi, that's just an amplitude with upside down, I guess. And then it says cosine kx over k squared, with the k being odd numbers, 1, 3, 5, and so on. So what we have in here is cosine of x divided by 1. Then we have cosine of 3x divided by 9. Then we have cosine 5x divided by 25. And everything is added here. Of course, this is sigma for adding. So we have all these functions added. So we come up with something similar to either one of these, but quite a bit more complicated and some kind of certain shape. So we're going to go to the graphing calculator and see how that is going to look like there. And this is what we would have to type into the calculator, where of course you recognize the pi over 2 minus 4 over pi times the sum sequence here is what substitutes for the summation sign, and then it goes in here cosine kx divided by k squared, and then the k is supposed to run from, well, 1 to what number. This here indicates infinity, but it would take the calculator forever by definition. So I decided to go from 1 to 15 in steps of 2. That ensures that we go 1, 3, 5, 7, so we just cover the odd numbers. Okay, let's do that on the graphing calculator. Okay. Let's see, where's my graphing calculator? At this point, let's see what happened here. I almost wanted to give up because my computer almost stalled. I hope this is going to work. Well, let me give it a try. I hope it's recording here. All right. So it said pi over 2 minus 4 over pi times, And now the sum sequence, you have to know a little bit more about the calculator. One sure way to find it is in the catalog, where everything is alphabetical. And then I'm going to hit my green S here, and then I go all the way down to, bummer, I think I'm going to hit my green T and go one up. So green T. And now it's not doing it. There we go. All right, there we go. There's the sum. That's what I wanted. And then the sequence I can also get from there. So second catalog. You also find that elsewhere. I believe you find that under stat or math or something like that. But this one here is in the catalog. You find everything that the calculator has. And there's the sequence that I wanted. And now it opens parentheses for the cosine. So cosine of k, that's alpha k, where did it go? There, times x. Parentheses, divide that cosine by alpha k squared, comma, alpha k, comma 1, comma 15, comma 2, parentheses. That's the, let's see how many parentheses I have to close. Oh, quite a few actually. No, I think just one more. The first one was for the sequence, the second one for the summation. Okay, go to window. And no, I don't want to graph between negative 100 and 100. So 0 to, let's make it 4 pi. Scale, I don't know if that really matters. And then y min, y max. Looks like we have an amplitude of 4 pi, which is roughly 1, and we have a vertical shift of pi over 2, which is 1.5. So maybe I want to be between negative 3 and 3. That should work okay. Actually, maybe negative 1 will work. Okay, let's see what we get. On a graph. It graphs really, really slow because it has to calculate a lot. I mean, after all, we put in all these odd k's. Oops, it's shooting up a little bit too high. Oh well. Because it has to calculate 8 different cosines running from 135 all the way through 15. That kind of looks like a triangle. Yeah, in fact it is. It's a triangle wave, so to say. And people who work in electronics encounter those and would be interested in these Fourier series. Okay, I just let a graph here. And then we're done with this lecture. Okay. Let's see if I can actually go over to where it started acting kind of funny earlier. And it works kind of funny for me right now, so I'm just going to stop right here.